Hello, I'm Parshana, and I will be covering one of CARP's 21 problems, specifically job sequencing. So let's get into it. So first, let's put it into context. In class, we've gone over load balancing. Load balancing was when we were given a set of jobs and we were given a set of machines, and we took those jobs and assigned it to those machines. Taking the next step after this would assume that load balancing has occurred. So we've assigned jobs to machines, and now we're going to focus on a singular machine, such that each job has an execution time, a deadline we want to meet, and if we do not meet that deadline, we incur a specific penalty. Our goal here is to figure out how we can order these jobs on this singular machine such that only one job can be processed at a time and all jobs must be processed. How are we going to keep the total penalty below a certain threshold? Now, taking this into mind, let's go into a formal definition. Job sequencing is a finite set of n jobs. You're given a finite set of n jobs, each with execution time t1 to tn, which are in the set of integers, the deadlines d1 to dn, penalties p1 to pn, and a positive integer k, which would be our threshold for our total penalty. This version is already a decision version given by CARP, where we say yes if there is a permutation W with this ordering of the jobs, all the jobs, such that to compute the total penalty, we take all of the jobs whose completion time is greater than the deadline for that specific job. We must take the penalty. We take the sum of all of the penalties by applying this to all of the jobs. And if that is less than or equal to k, we have given a valid permutation of W that satisfies this. Let's go into an example because that was a little dense. So let's assume that we are given 3 jobs, each with an execution time, a deadline, and a penalty, as well as a k threshold of 10. So our total penalty must be below or equal to 10. So let's take this ordering, where we schedule job 1, job 2, and then job 3. It would look something like this, where job 1 finishes by time 3, job 2 finishes by time 5, and job 3 finishes by time 7, assuming it's within those execution times. So since job 1 finished within its deadline of 3, there's no penalty that occurs. Job 2 finished by time 5, which is greater than its deadline, so we incur this penalty of 5. Job 3 finished at time 7, which is also above its deadline, so the penalty 7 gets assigned. So we take the sum of all of the jobs and the penalties if it's 0 or a value. We take 5 plus 7, we get 12, which happens to be greater than our threshold. So this is not a valid permutation that satisfies job sequencing. Then let's look at this one. This ordering is where we put job 2 first, and then job 3 first, and then job 1 first on this machine. We can see that job 2 finishes by time 2, which happens to be within its deadline of 4, so no penalty occurs. Job 3 finishes by time 4, which is within the deadline, or by the deadline, so no penalty has occurred. Job 1 finishes by time 7, which is past its deadline of 3, and thus a penalty of 10 is applied. Then, as again, we take the summation, we get 10, that's less than or equal to k. This is a valid sequencing, a valid permutation solution. Now let's see if job sequencing is an in NP. To show this, we would need to provide a polynomial time checking algorithm, which we've provided here. We take as input a set of n jobs with execution times t1 to tn. We take deadlines d1 to dn and penalties p1 to pn, a positive integer k, and a possible solution of a permutation w. And we return true if you take the sum of all of the penalties, the total penalty, and if that is less than or equal to k, that is true. Otherwise, it is false. The way that the code essentially works is we have a running total for our penalty and a running cumulative time. If we take the sum, if we go across all of the jobs in our solution, in the ordering that it's provided in, and we add the cumulative time along the way, which is just adding the execution times. If we see that the cumulative time is greater than the deadline for that provided job, we will add the penalty for that job. Otherwise, we do not add it. If the total penalty, because we want to presumably end early if possible, if it is greater than our K, we can prematurely just end and return false. Otherwise, if the total penalty is greater than K after we've gone through all the jobs, similar case, we return false because it does not satisfy. Otherwise, we return true, meaning that we have provided a solution whose total penalty is less than or equal to K. We know that the running time of this algorithm is polynomial as we go through the set of jobs in W one time. And we only have if statements, no nested for loops. So we know that the total running time for this is O of N. Next, let's look at if job sequencing is in NP complete. To do this, we'll provide a reduction using knapsack without repetition. I'd like to emphasize that we're using the without repetition version because we want to ensure that we're not choosing the same item multiple times, just like we wouldn't in job sequencing choose the same job multiple times. So just as a refresher, what is knapsack? Knapsack is a set of n items, each with weight W1 to Wn and value V1 to Vn. We're given a threshold W and we introduce a value V. Our solution or our output will be a subset S of distinct items, so not choosing multiple times, such that the summation of the weights is less than or equal to W, our threshold, and our introduced threshold is, if you take the sum of all of the values of our solution, should be greater than or equal to V. So by doing this, we're saying a reduction of knapsack to job sequencing, if exists, implies that job sequencing is at least as hard as knapsack. So let's show it. So here's the reduction from knapsack to job sequencing. We are going to take I, which is the instance of knapsack, with the following parameters. N will be our set of items, 1 to lowercase n. W, lowercase w, is our set of all of our weights, W1 to Wn. V is the set of V1 to Vn of the value. Our capital W, which is the part that we need to be less than or equal to. And then V, which is our value that we want to be greater than or equal to. Taking this instance of knapsack, we're going to convert it into a valid input of job sequencing. So we're going to treat our items as one-to-one with our jobs. So n jobs, n items. We're going to have our execution time be the set W, lowercase w, of the weights. We're going to have D, which is our deadline, be the set where we take just basically what capital W is and then make an equivalent amount such that is W to Wn, or to W, with n total items. And then our penalty is going to be similar to our value. So we're just going to take that set. And lastly, for our K, we're going to say that that is the summation of all of the values, or all of the penalties, minus V, which is the value we want to be greater than or equal to. Before I move on to the next step, I want to introduce how we came about that and why it's important. So this is essentially saying, if we take the two problems side by side, knapsack is in charge of maximizing V. Job sequencing is important because we want to minimize K. So there's kind of an inverse relationship there, where knapsack, we want to choose items that give the most value, where job sequencing, we would prefer lower penalties. Where if you finish a job after a deadline, you're losing the value. So you have to thus do the opposite, which is pay the penalty. If you finish a job before the deadline, you get to keep the value. There's no penalty. So for knapsack, we must gain at least V, and job sequencing, we must not lose more than V. So as V increases, K decreases. And thus, that's how we came up with this. So now let's move on to the next step, where we will suppose that there is a polynomial time algorithm for job sequencing that returns a permutation S. And for knapsack, thus, our solution will be taking this out into longer form, where if you take the completion times that completed by the deadline D, or otherwise known as W, if you take all of the jobs that completed by the deadline, that will be our solution for knapsack. And further, if there is no solution for job sequencing, there is no solution for knapsack. So let's go through an example so we can see how this works. So let's take an instance of knapsack where we have items 1 to 3 with a given weight, a given value, a capital W, and a capital V. Just to speed run this process, we can see that if you were to choose item 1 and to choose item 2, the sum of its weights would be within capital W, and the sum of its values would be within V. Thus, choosing 1 and 2 is a valid knapsack where we are within the bounds. Now, if I were to translate knapsack to job sequencing, it would be as follows, where you can follow the color scheme. So if I take the items 1, 2, and 3, that will be 1-to-1 with the jobs 1, 2, and 3. Our weight 2, 3, 4 will just be our execution time 2, 3, 4. Our value 6, 4, 5 will be our penalty 6, 4, 5. We will take capital W and assign it as a deadline. Something also I forgot to note is that for this version of knapsack job sequencing, the job sequencing, of course, has a very strict same number. In other versions of this, we would probably see we'd see different deadlines. So going back, our K is going to be the sum of all of our penalties, or the sum of all of our values, minus our capital V, which is 10, and we get 5. If we were to produce a solution then for job sequencing, where we do the order, say, for example, in 1, 2, and 3, just to skip through a little bit, we will see that job 1 and job 2 finish on time by its deadline, and job 3 does not finish by its time, incurs a penalty. And we see that the penalty, though, is within our bounds of our threshold K. We can see further that the on-time jobs are 1 and 2, and the late jobs are 3. So this was with the assumption that if we took these two times, which are the completion times, we are within the deadline. And going back, we can see that the on-time jobs are 1 and 2. Similarly, for knapsack, the on-time jobs were 1 and 2, which is why when we go through this, we can see that if we were to take all the jobs that completed on time, that would be our solution. Now to actually prove that this exists and this works. So if we are given an instance I of knapsack that produces a subset H of S, if and only if the instance that f of I of job sequencing produces a permutation S. So let's prove the forward way first. We're going to assume that knapsack produces an H of S solution with the bounds of this, where the sum of all of the weights of the solution must be less than or equal to W. And the summation of all the values of the solution must be greater than or equal to V. Further, we're going to assume that we do get a solution or permutation S from job sequencing, where it's scheduling all the jobs by polynomial time algorithm. We thus want to prove that the total penalty will be less than or equal to K. So how will we do that? If we take all of the jobs in S, meaning all of the jobs produced by job sequencing that finished within the deadline, so the total completion time for that job is less than or equal to W, we're going to assign it to set E. So just to reword that, set E will contain all of the jobs that finished within the deadline. Similarly, we're going to go through all the jobs that didn't finish within the deadline and assign that to set F. So set E are all the jobs that finished within the deadline. Set F did not fail to meet the deadline. The total penalty will thus be all of the jobs that didn't finish on time, because all the jobs that did finish in time will incur no penalty. So if I take the sum of all right here, of all of the values, and I subtract it by the sum of all of the values in the set E, keeping in mind set E, ones that did finish in time, we get P of I, which is all of the values in F. Kind of intuitively, if you take all of because we are splitting those sets into E and F, the summation of both of those sets would have to be all of the values. From what we have seen, we know this formula exists, and we can thus say that we can substitute this value right here as capital V, which is equal to K. Awesome. We have now proven that the total penalty is less than or equal to K. Now let's do this in the backwards direction. So we're going to assume that there is a solution to job sequencing S, which is a permutation whose penalty is less than or equal to K. Further, we're going to assume there exists a solution H of S, where H of S is if you're to take the set produced by job sequencing, go through all the items, and take all of the jobs whose completion time is within the deadline. That is our solution for knapsack. We want to prove that the W of I, the sum of WI for the solution of knapsack is less than or equal to W, and that the summation of all the values of the solution are greater than or equal to V. So we know that the total penalty paid are all of the items, or all of the jobs that are not within knapsack, because knapsack, the solution is all of the values that did complete on time. So we want to take all the values that didn't complete on time, which would be the ones that are not in our solution for knapsack. So similar to before, we take all of the values, V, we subtract it by all the values that did complete on time, which will be less than or equal to K. If I rearrange this by moving this to the other side and moving this to the other side, I get the following, where this is exactly what we saw before, just rearranged, where we said K equals the summation of and sum of the values minus V. Now it's switched, and ta-da, we have proved that the values of the solution of knapsack are greater than or equal to V. Now let's prove the second part with W. So further, if we take all of the jobs of H of S, these are all of the jobs that finished within the deadline. This means that the sum of all the weights, which we made a one-to-one relationship with the T, sorry, this N shouldn't be here. If we take all of those weights and all of those times, there's a one-to-one relationship, so we say they're equal. We know that they are less than or equal to W, because the summation of all those times, kind of like how we showed in our checking algorithm, was the way we were calculating the cumulative time was by adding the times, so of the execution times. So we know that is less than or equal to W because we say that H of S are the jobs that finished in time. Thus, we have shown that W of I, the summation, is in fact less than or equal to W. And we have proved what we wanted to. Lastly, are some fun applications. I was recently watching a film, and I thought it was cool to introduce the idea of using a similar set. So if you have a set where you, for a movie, want to shoot a series of scenes, and you know that each scene will take a certain amount of time to shoot, and your goal is to reach a certain time for those shoots that you want to do, to make sure that you can send it to the editing team, where if you are unable to meet that deadline, you have to pay overtime to the editing team. And some companies don't want to provide the overtime. So being able to successfully organize how you want to shoot for the set. And a more practical example we might see in everyday life is delivering food orders for a restaurant. So if you are given a series of customer orders that are provided, and the execution time is the time it would take to cook all those orders, and our deadline is the assumption that we want to make sure that those customers get the promised time that we said that the food would be ready by. And if we can't meet that deadline, maybe we have to provide a penalty, maybe we get a bad review, or maybe we have to give a discount. So being able to best organize those jobs where you can only cook one thing at a time with that assumption, being able to meet that. And awesome. Thank you so much for listening.